Imagine you're watching the season finale of your favorite show, maybe Game of Thrones at midnight, and suddenly Netflix crashes. 47 millions are trying to access the same server. This has actually happened, and the solution is data partitioning. If you miss this concept, you'll miss out 30% of your system design interview. Earlier, there used to be a time when there used to be only one server. So during one server, suddenly there's a spike of requests. Maybe 47 million requests has come. And because of that, the server crashes. Now there came the partitioning strategy. Instead of one server, we now keep three servers. So the load of 47 million users is equally distributed. So server 1 will have 15 million, then server 2 will have 16 million, server 3 will have 16 million. That way, the load is equally distributed among three different servers. That is how the load is balanced and the optimizations of read and write happens. This is what happens in data partitioning. Now we will understand why partitioning matters. Your database is like your phone storage. Remember, you had a time when you had 10,000 photos and your phone became unavailable. That's exactly what happens at data scale. At MAANG interviews, they'll ask you to solve it in 45 minutes. Okay, there was time when we did not used to have data partitioning or data indexing in different databases. So the problems there were scalability limit. Because of single database, it has its limit. Suppose the limit of a database is 1 terabyte. Now, because of single DB, if it reaches its max, it will stop storing data. Now, what we need to do is add another DB. And inherently, because of the size of a single DB reaches 1 TB, the queries will become very slow. Reason is that suppose you want to do a range query. Maybe you want to search a data within the range or a date range of 1 month. To search data of 1 month, and that also in applications like Instagram or Facebook. So it will take a lot of time, at least 30 seconds for 1 billion record. Because of that, there will be very slow queries, the response will be very bad, and it will add on to a very bad user experience. Sometimes what happens is that because of just one type of database, if a database goes down or crashes, then there is no availability. In any how you cannot get the data. That is one of the major drawbacks when we used to have single partition. Now, after getting the partition, we solve many problems. We can do parallel processing. We can handle multiple read queries at the same time. They can look into different partitions at the same time. That way, it increases the throughput of the system. The faster queries. We can have indexing within the partitioning, different types of keys or indexes. Because of that, we can do faster queries and high availability. Since we are having multiple partition, we are also keeping replicas of the partition in different partition itself. Suppose of partition 1, we keep the replica in 3 different partitions. That way, whenever one partition goes down, we haven't lost any data. We have a replication or a copy of that data in another partition. For the time being, the query will not query partition 1, but it will search in partition 2 or partition 3. That is how we are solving many problems when we introduce partitioning. And that's the beauty of it. Now you will ask, are there multiple types of partition strategies, or can we do it in just one format? The answer is we have multiple strategies. Today I'm going to discuss about the 3 partition strategies. So let's start with the first partition strategy, that is key range strategy. So how does a library organize millions of books, that is A to M on the left, then N to Z on the right? Google uses this exact same strategy for billions of searches. This is called range partitioning. It's asked in around 8 out of 10 system design interviews. Now, if you see in this diagram, we are describing key range partitioning, or you can say range-based partitioning. So partition 1 has a range from A to F. All the people with last names starting between A to F are stored in partition 1. Then partition 2 has all the names starting in the range G to M in partition 2. Similarly, in partition 3, all the names starting between N to Z are stored in partition 3. This is how we divide the partition based upon the key, and we design the range such that it becomes easy to search and store data. Some of the pros of this is that the range queries are efficient. It is easy to understand and design. Now the cons is the data can be unevenly distributed. Suppose many names fall in the range G to M. Most of the last names are starting from G to M in particular region or particular country. That way, one partitions become very heavy, but other partitions are light, and the load also is very heavy on partition 2. So that is why it can be a problem if one type of names are too much, and it can create a load over one partition than other partitions. How does Instagram handles 2 billion users? Instagram has around 2 billion users. If they use alphabetical partitioning, the S server would explode. Like Smith, Singh, Santos, they all will lie in the S server. So they use a trick called hash partitioning. Now in a hash partitioning, we have a hash key. The hash key can be SHA-256 or many other algorithms that are available. And we put the key. So key can be the name which we are going to partition. Suppose in the previous example, we were using the last name. We will take the last name as a key, do a hash around it, and find the hash over it. Now, if we have 4 partitions, in that case, we will mod it by number of partitions. So user Smith hashed is equal to 8472. Create a mod out of it, it will be redirected to partition 0. Similarly, user Zhang, it is hashed to 3391. So what do? We take a mod out of it and suppose it falls into partition 2. That way, we evenly distribute all the names into even number of partitions. That way, the load is distributed. Now, some of the pros is we are able to evenly distribute the load. Because of that, there is no hotspot. Now, the problem with this is that what if I want to do range queries? Because of the range queries, I still need to query in multiple partitions. For example, if I'm finding the range between A to Z, I want all the partitions to be queried. In that case, it will become a bottleneck for this. That is why hash-based partitioning is also not one of the best approaches to use. So we will discuss the next problem now, the celebrity problem. When Elon Musk tweets, around 150 users rush to see what he has written. All the requests hits one partition and the Twitter crashes. This is called a hotspot problem. And if you can't solve it in your interview, you won't get the offer. Let me explain how the hotspot problems look like. Like I told, when Elon Musk tweets, it goes to a single partition. Now going to the single partition will overload one partition and the other partition will remain happy, cool, no load is over there. Now the overloaded partition will make the system very slow and the response will be very slow in this case. So there are 3 solutions which we can do. One is when there is a celebrity or we know that particular user's tweet will attract many users. In that case, what we can do is we can simply add a random number plus the celebrity ID and then hash it. That way, it will be evenly distributed among different servers. Adding a random number does the trick for us. It will evenly distribute the data among the partitions, and that way we can reduce the load on a particular one server. There is one more solution which we can have. If we know a person is a celebrity and he has a lot of following, in that case, we can have a dedicated partition for that particular user. People who have millions and billions of followers, they can have a dedicated partition. So it will be like a celebrity data, and we can have a separate cluster for them. That way it reduces the load on the partition where there are normal users like you and me. And the third approach is cache them. We know certain tweet will be accessed more. As we realize after a tweet, suddenly a video goes viral. Or we know that some type of tweet, like for a celebrity problem case, it will be viral and many people will be reading it. We can cache those eventually. As soon as a video or a text or a post is about to be viral, we immediately cache it into multiple geolocations, and that way we can share the load and it will not affect the user experience. So this is what a hotspot problem is and how we can solve it. Now you can search Amazon by price, then rating, then categories, by brand name. But the data is partitioned by product ID. And how does it work? This is because of secondary indexes. If you get this wrong in the interviews, you'll fail the Amazon round. So it's not just simple partitioning we do. When we need to search based upon these many categories, we need a special type of partitioning, and that is called secondary indexes. Let's discuss one of the type called document-based partitioning in secondary index. Now suppose you have partitioned the shopping list or the products in Amazon by product IDs. So product IDs from 1 to 1000 is stored in partition 1, and product IDs more than 1000 are stored in partition 2. Suppose if you want to find all the electronics whose price is under $550, what will you do? You'll eventually have to search all the partitions and then find those. The best way is to do the secondary indexing. So there are two things what we do here. One is we store the data from 1 to 1000 in partition 1 and the later data in partition 2 as it is, like the strategy which we discussed earlier on. Along with that, we create a local index. We store the data by category. We store the data by price in all the partitions. Similarly, we store the data by category here. So this is called local partition. We create a partition from the data we already have in that specific partition. That way, it will become easy to search among the partition. We can easily do binary search. So for example, in this case, when we want to find electronics under 550, what we will do is we'll go to partition 1 and then we will do a binary search or a range-based search and get all the products that are below $550. Similarly, we'll go to partition 2 and then we will get a data which is lesser than 550. The search will become easier. We don't have to go to each and every row and then search it. But do you see a problem over here? Yeah, we still have to search in every partition. How can we make this much more faster, much easier to load? Now, Google doesn't search every server for your query. If it starts searching every server for your query, it will crash down and the user experience will be very bad. They use term-based indexes. This makes the search 100x faster and its favorite interview question at Google. Let me show you how the term-based indexing happens. It is also a type of secondary indexing, and this is far more better than simple document-based indexing. Same example of Amazon. We'll store all the categories between A to M in partition 1. Then we'll store all the categories between N to Zen in partition 2. That's the simple. That we understand. We are using hashing and then we'll store it. Now instead of locally storing all the ranges within a partition, we will store all the categories of electronics in partition 1. Similarly, we'll store all the products and the category books in partition 1. Now in partition 2, we will randomly take another category, for example sports, and we will store it in partition 2 and toys in partition 2. That way, along with the data for partition, we are storing a global level of indexing. We are storing all the data of electronics in one partition. The advantage here is that Now you will need to search only in one partition instead of going into all the partitions. How the reads become faster because now we only need to search in one partition. Now what about the problem? I guess you've already learned it by now. If we write, first we'll have to write in one partition where it belongs to, and then we'll have to write into another partition where the category or the secondary index is happening. So the writes might become slower, but the reads become super fast now. So this is primarily used in DynamoDB. So now you see how secondary indexing can help us increase the reads much more faster and how Google uses it. Okay, now how Netflix adds servers without downtime. Netflix adds around 100 new servers every month, but they can't just shut down the server. How do they move the data without anyone watching or noticing? It's called rebalancing. This question appears in every senior level engineering interview. So every day or every month, there might be servers that go crash. You need to replace those servers and then rebalance the data. And you cannot even see it, you cannot notice it. How does that happen? This is because of rebalancing strategies that we are going to discuss now. Now in a default based partitioning, where we do the hash key and then mod it by the number of partition and we redirect it to the relevant partition. It can be a bad strategy if we add new partition. Suppose out of 4 partition, we decide that there can be 5 partitions now. In that case, when we add one more partition, we'll have to redistribute data out of all the partitions, and then we'll have to change the read logic and everything. It is like a very cumbersome process, and in that case, we'll have to stop some of the partitions. Now that is a problem. Another better approach is to use consistent hashing. Now, consistent hashing is a better approach than to use a simple hash strategy. So what we'll do is, we'll use the same example. We'll have 4 servers. Now 0, 1, 2, and 3. We start from 0, but these are 4. So what we'll do is here is whatever the hash values that are found in this specific range, we will put it into the server that is towards the right of that value. So if we are having in a hash range between maybe 1 to 179, in that case we will see which is the next server to it. So here we see that the server is at this point. We will put it into this server. Similarly, whatever are the values found in this range, we will put it into the next server that is towards the right of that server. So we'll put it here. Now what will happen if we introduce another server? Maybe over here we introduce server number S5. If we introduce one more server, in this case we just need to distribute the data between these 2 servers. We don't need to distribute it among all the servers. So that will solve our problem of redistributing all the data, where we use a simple hash strategy. Now that covers the redistributing of data among different partitions. You have 4 servers in this case. Do you think that for 4 servers we will have only 4 partitions? No, that's wrong. Actually, we can have multiple partitions in every server. In this case, let's say we have 1000 partitions over 10 servers. So we can equally divide the number of partitions in 10 servers. So for each server, we will have around 100 partitions. That way, it is easy to move the entire partitions into different nodes. Suppose partition 1 goes down and we introduce one more partition. We can easily move those specific partition in partition 5 or a new partition. Or for instance, we have a new node that is being introduced as a server. We can now equally divide those 1000 partitions or those 100 partitions among 5 servers. But the number of partitions here remains fixed. The second type is dynamic partition. So dynamic partition is like a B plus tree. In B plus tree, what we do, whenever there is the limit, okay, so for example, the data limit is 4. Now each partition can have only 4 data. So what we will do here is, we will create 4 data here. 1, 2, 3. So when it reaches 4, we will divide this partition equally. So now we will have 2 partitions. Each partition will have 2 data. You see how it happens? It's just like B plus tree. Whenever we reach a limit, we will divide it into more partitions and that are equally distributed. Whenever the data grows too large, we'll split the partition. This is primarily used in HBase and MongoDB. The third approach, and it's the most robust approach, it's called proportional partitions. For example, we introduce a new node in the server. Earlier there were 4 nodes. We have introduced one more node. Now we will equally distribute the data among the 5 servers. So that way the load will decrease over one partition. This is called proportional partition. It depends upon the number of nodes. As the number of nodes decreases or increases, we will equally distribute and the size of the partition will also change based upon the number of nodes we have. So that is why it is proportional to the number of nodes. It is primarily used by Cassandra. So now you see how we use rebalancing strategies, and if you talk about these in the interviews, of course you've reached a L5 plus level, you can easily track staff or staff plus roles. Now we come one of the most interesting part of data partitioning. How do we route different requests to different partitions? When you type amazon.com/product/product ID, how does the request find the right server among 10,000 servers? It's called request routing. And if you miss this, your system design will be a critical flaw. Now let me take an example of how it works. Okay, now let's discuss about some of the request routing strategies. I'll discuss 3 of them, and those are most popularly used in all the system designs. Now the first type is called client-side routing. In client-side routing, all the logics of partitions are stored at the client end. When the request comes, the client itself calculates which is the partition it needs to query, and it will directly query that specific server. So in this case, if you see, the client automatically calculates that it has to query on server 3. So it will do all the logic here and then call the server 3. The best part is that there is no extra hop, but the problem is with the extra complexity. Whenever there is change in the partition logic or wherever there is a problem in the partition, then we'll have to update the client logic on every client, and there can be millions of clients. So it's not very scalable solution to have a client logic updated every while when the partition changes, and that happens quite few. So it won't be the best approach, but it is still an approach where there are lesser number of clients. The second is the routing tier, the load balancer. We've seen in many of the system design interviews that you introduce a load balancer which will redirect your request. Why don't we also include the logic within the load balancer? Sometimes there are use cases where we add HA proxy within the load balancer. That way, we move the load from the client to the load balancer. That is, the logic is now added to the load balancer. We will have lesser place to update now. We'll only have to update the load balancer here. Although the extra hop will still remain there because we are adding now the logic to the load balancer. And if there are multiple load balancer within the system, then we will have to update those logics here. But the advantage is the clients become simple now. We don't have to update the logic within the client, and it is much more secure because load balancer is within the server and we have more control over it. But still, it is still much more slower. The third approach is the most modern approach, and it is much more faster. That is by using the gossip protocol. Even Google uses it. We use it in ZooKeeper. The client sends a request to the load balancer. Now randomly the load balancer decides to send the request to server 1. All the logic of the partitions here is stored in all the partitions. Server 1 realizes that it does not have that information, but it knows which server has the information. So it will redirect to server 2 because it knows server 2 has the information. Here in this case, we will store all the logic of all the partitions in every partition. That way we will have a less of an extra hop. So this way we will track all the partition assignments and all the servers know the cluster state. This is used by Kafka, Edgebase, and one of the modern routing algorithms, and even ZooKeeper. So always mention the ZooKeeper in this type of questions. And this is how you solve request routing of a highly scalable system. Now we have discussed so many strategies of partitioning, how the partition happens, how it scales, now where it is actually used, how will you face it in an interview. So let me take an example where the partitioning logic will be much more useful as compared to other concepts of advanced system design. So here's a question where the understanding of partition helps you a lot. It's called URL shortener. Now this is one of the examples, there can be other examples also. So you got a requirement that you need to have 10,000 per second writes, then 100,000 reads per second, then 1 billion URLs to be distributed. So in a URL shortener, the first strategy will be to decide the partitioning strategy. You will decide which type of partition to use. Maybe in this case, it's using hashing of the short URL and divide among the number of partitions to evenly distribute the data. Second step will be to find the number of partitions, how many partitions we want to create. So if there are 1 billion URLs and there are 100 million URLs that you can store per partition, so you will simply divide it and then you will find out that we need 10 partitions. Next step will be to use of the secondary index. Secondary index, as you know, makes the search much more faster. In this case, we can use document-based indexing that will make the queries much faster. Fourth thing is rebalancing. As we discussed previously, how do we rebalance the data, how all the requests are routing, how we can route particular customers' requests much more faster. We can use fixed partition routing strategy, which are total of 100 partitions. That way we can easily scale the data. Fifth step is request routing. In that we can talk about the load balancer and ZooKeeper approach that tracks the partition's location in every server. And the sixth thing is we can talk about the hotspot. This is one of the conditions that can come up. So here you can discuss about the caching layer logic, and then how do we solve the scalability problem, which we have discussed in the previous videos that we have discussed. So this is the final architecture. The client requests the load balancer. First, it will check with the ZooKeeper which Redis or which cluster to read from. Then it will go to that Redis cache. If it has the data, it will revert back. If there is a cache miss, then it will go to a specific partition using different strategies that we have discussed above. So now this is the problem which gives you the offer. And if you discuss about different partition strategies, you are there, you've got the offer. So I hope now the partitioning concept is much more clear to you. Now if you've used partition in your daily work, do comment about what kind of partitioning strategies, what kind of request routing, what kind of rebalancing approach you are using at your company. Maybe we can discuss further about that. Thanks, and do comment about that.